Okay, so hello everyone. Today we're going to start talking about intersection theory. So today we're just going to go over the prerequisites. So intersection theory. Well, the first subtopic is we are going to talk about manifolds with boundary. And orientation. So this is something that you might or might not have seen on a class about manifolds. So it's slightly more advanced, but not a lot more. So, but yeah, so that's why, but I'm going to review it and try to go as slow as possible so that everybody's on the same page. And then we're going to really talk about intersection theory more next time. Okay, so first of all, we have to say what a topological manifold with boundary is. So a topological manifold with boundary is a second countable Hausdorff topological space such that every point B in X has a neighborhood which is homeomorphic to an open set in what I'm going to call Hn. So that's the upper half space. So that means the set of points x1 through xn in Rn such that the last coordinate xn is greater than or equal to 0. Actually, let me do something different. Let me just do the first coordinate. It's bigger than or equal to 0. It's the same. Okay, so lemma. Well, actually, let me just, draw a picture. So, this is your Hn. Here's a picture in the two-dimensional case. So basically, I have a manifold with boundary is a topological space with these properties, second countable Hausdorff, such that every point has a neighborhood which is homeomorphic to an open set. So what's an open set in Hn? Well, if I'm in here, if my first coordinate is positive, then an open set is just this without the boundary here. But if I'm over here, an open set it's a relatively open set. So it's an open set in Hn. So this is an open set. Okay, and then you're led to just looking at this picture, it looks like there are two kinds of points. And that's the lemma that I'm going to state now, that indeed there are two kinds of points. So lemma, let X be a topological manifold with boundary with this, so that means this definition, and let P be a point in X, and phi and psi from U to Hn be charts. Around P. Okay, so suppose that phi of P, that phi of P is 0 and then something something. Then psi of P is also going to be 0 and then something something. Okay, so that means, if the first coordinate of one of the charts is 0, then for whichever other chart, it has to have the same property. So, in particular, so that means, in particular, that you can't have a chart that takes a point. So if this is my manifold M, and say, I'm over here, this is a point P, and by one chart, I take it to this point here. And if I take another chart, psi, I cannot take this to a point here. This is not possible. You see, it's basically an if and only if, because I can just choose the other chart. I can, to prove the lemma implies an if and only if. Okay? So that's the lemma. How do you prove this? It's actually, the proof is not very hard, but if you don't know algebraic topology, then maybe it's not as easy as it seems. So if you know a little bit of algebraic topology, like homotopy groups, for example, or homology groups, then the proof is pretty easy, because basically, if you take your point P and if you look at the transition map, psi composed with phi inverse, that's going to be a map from Hn to Hn, from a neighborhood of P to a neighborhood of P. So from, say, phi of u to psi of u, where u is a small neighborhood, is a neighborhood of P in X. And then if you remove P, then you have a homeomorphism from an open set. If you remove phi of P and you remove psi of P, then you have a homeomorphism from an open set of Rn to an open set of Rn. An open set in Hn to an open set in Hn. But anyway, it's a homeomorphism of subsets of Rn. So now, if you know enough about homeomorphisms of open set of sets in Rn, then you're done. So basically, if phi of P has the first coordinate 0, then when you look at this guy, phi of u minus phi of P, then this is contractible. And if psi of u, if psi of P is of the form x1 tilde xn tilde, where x1 tilde is different from 0, then psi of u minus psi of P is not contractible. In fact, it is homotopy equivalent to a sphere Sn-1. So if there's a homomorphism, you have a problem here. And to show you have a problem here, without algebraic topology, it's maybe a little bit harder. But maybe it's not so, I guess, plus a little algebraic topology. Okay, so let me just draw the picture. So if you are taken to a point here and you look at a neighborhood and you remove this point, then you have something that is contractible. So this is the case for phi. And if you suppose, by contradiction, that psi of P is taken to the interior of HP, so the first coordinate is different from 0, then when you look at a neighborhood and you remove the point, that's homotopy equivalent to a sphere. Okay, so you can, it's deformation equivalent, so you can deform this punctured ball into a sphere. Okay, and these cannot be homeomorphic. Okay, so to prove it's not homeomorphic is maybe a little bit tricky without algebraic topology, but with a little algebraic topology you can prove it. So I guess I'm going to leave this last little bit for you to think about. Okay, any questions? So what this leads us to is now we can actually define what the interior and what the boundary of a manifold with boundary are. So the boundary, if X is a manifold with boundary, so definition, let X be a topological manifold with boundary. Then we can define the boundary of X to be the set of points such that there exists a chart around P such that phi of P equals x1, equals 0, x2, xn. So this is the boundary. And the interior is everything that's not the boundary. So it's the same thing as saying that it's a set of points in X such that there exists a chart around P such that phi of P is equal to x1, etc., xn, where x1 is different from 0. Okay. And by this previous lemma, these two sets, they are disjoint, and the union is indeed X. Okay? Any questions about this? And so one interesting observation is that the interior of X and the boundary of X are manifolds, are topological manifolds. Topological manifolds without boundary. So in the usual way of dimensions n and n minus 1 respectively. Okay, so this is very easy to see that if you're an interior point, then a neighborhood, an open neighborhood in HN, you can make it small enough so it's actually an open neighborhood, an open set of Rn. And if you're on the boundary, so if you're here where x1 is equal to 0, then like over here, then the intersection of an open neighborhood in HN with this Rn minus 1 is just an open neighborhood in Rn minus 1. Okay, so that's why the boundary of X is also a topological manifold. Okay? All right, so now let's talk about, so far we've only talked about topological manifolds with boundaries, so now we need to say what's a smooth structure on HN. So definition. A map from an open set in HN to HN is called smooth if this is the definition of being smooth. So if it admits, if it admits a smooth extension to a map F tilde from U tilde to Rn, where U tilde contains U and is an open set in Rn, where U tilde is an open set in Rn. Okay. So U is an open set in HN, so it's relatively open in Rn, but it's not open necessarily. So, if I have a map from HN to HN, what I say it's smooth if I can actually extend it a little bit for all the points like on the boundary of HN. Okay, so if it's like coming with like infinite derivative, then it can't be smooth in particular. Okay. So any questions about this? So that's basically the definition that we need to talk about what a smooth structure in a manifold is. So if we know what it means for a function to be smooth, then we can talk about the transition functions. So if we have these charts for a topological manifold, then we can look at the transition functions and we say that the charts are compatible if the transition functions are smooth. And then an atlas. So I guess let me say this. We say that two charts phi from U in X to Hn and psi from V in X to Hn are compatible if the transition function, so restricted to phi of U intersected V, is smooth. Okay, and as usual, we'll say an atlas is a collection of charts whose domains cover X. Okay, so now we can define what it means, what a smooth manifold with boundary is. So a smooth manifold with boundary is a topological manifold with boundary endowed with a maximal smooth atlas. So the smooth, as usual, I'm going to write in parentheses. So if I don't say that it's smooth, then it is smooth, by assumption. Okay. So we're going to mostly just talk about smooth manifold with boundary. Okay, so that means that you're choosing a particular smooth atlas. And if the manifold doesn't have boundary, then it's actually quite hard to change the smooth structure. So it's possible for many manifolds, especially in higher dimensions, but it's very tricky. Like usually when you think of a manifold that's naturally given, it comes with a smooth structure. And it's very difficult to construct another smooth structure, and even harder to show that these are different when they are. So it's possible to do that, for Rn, for n sufficiently large, for spheres, but it's pretty tricky. But for manifolds with boundary, for topological manifolds with boundary, it's actually quite easy to change the smooth structure on the boundary at least. So for example, if I give, so here's an interesting example. So let's just say I look at a disk. So it's easy to see that a disk, is a topological manifold with boundary. And if you just see it as the unit disk inside of R2, that gives you the smooth structure in R2 induces a smooth structure here. You just take like the inclusion of every point of a neighborhood, of a relatively open neighborhood of S2 into R2 as your chart. And that will give you an atlas for the disk. But now you could consider the homeomorphism that takes the disk to a square, for example. And now if you compose your chart from here to here, then at these corners here, you're going to have a problem with smoothness. Because basically, well, if you consider these the charts, then you're still a smooth map. But if you look at the inclusion, if you kind of forget this homeomorphism and you look at the square contained in R2 and you play the same game here and you just look at the inclusion maps, then this will not give you the structure of a manifold with boundary, a smooth manifold with boundary anymore, because you have these corners here. Okay? So in other words, I guess one way to see this is that if you have a smooth manifold with boundary, that induces a smooth structure on the boundary. So a smooth manifold with boundary, manifold with boundary. So if X is a smooth manifold with boundary, then the interior of X and the boundary of X are also smooth manifolds. So they have an induced smooth structure without boundary. And here, that's not the case. So if you look at the square here, which is the boundary, which is on the boundary of this guy, if you consider the structure, if you try to put the smooth structure that's just the inclusion, this square is not going to be a smooth manifold with the induced with this inclusion. Okay, because this guy here is not diffeomorphic to a line, to an open set on the line. Or not. Okay, so that's, you see that, choosing a smooth structure is kind of subtle, but, that even, yeah. Sorry, what I wanted to say is that not that you can easily change the smooth structure, but that choosing a smooth structure with boundary is a little on a manifold with boundary can be a little bit subtle. Okay. All right. So I guess another example in higher dimensions of this is you can just look at the ball. It's a very important example, very easy, but very important. So then the set of points whose norm is less than or equal to 1. So that if you look at the natural inclusion of that into Rn, this is a manifold. Manifold with boundary, and the boundary is another very famous manifold, which is the sphere of dimension n-1. Okay? So as before, you can ask yourself, so how do I construct manifolds with boundary? It's not so easy to define a manifold in general by the definition, but I guess the first way to produce a huge number of manifolds with boundary is just very similar to producing manifolds. So to produce manifolds, you take a smooth function, you pick a regular value, and you look at the pre-image of the regular value. So to produce a manifold with boundary, what you can do is you can consider, so this is the proposition, you can pick a smooth function on a given manifold. You could start with Rn if you want. And you pick a regular value, a regular value. And then now what you can do, I don't know, then now you can look at the pre-image of, say, A plus infinity. So everything that's above A, or everything that's below A, I guess. And you can look at the pre-image of minus infinity A. Either thing. This is a manifold. These are manifolds with boundary. Manifolds with boundary. And the boundary is just, for both of them, the boundary is just the pre-image of A, which we already knew was a manifold. Okay? Well, let me write it like this. Over here. Any questions about this statement? So this is exactly the same thing that we did for the ball, so it's a generalization of the ball. So the ball satisfies this for the function norm squared. Okay, so how do we prove this? Well, first of all, if you just take I'm going to prove for this one, for the first one, but it's the same, very similar for the second one. It's almost the same thing. So let's start with the first one. Well, let's just prove the first one. First of all, if you take a plus infinity, that's an open subset here. So the preimage of a plus infinity is an open set of X. So therefore, every open set of a manifold is a manifold of the same dimension. So, this guy here is a manifold without boundary. So what we need to do is we need to look at the points that are whose image is A. So now we have to look at really what happens for the points that are on the preimage of A. And we have to show that over there, for these points, we actually can find a chart that takes values in Hn. Okay? So if we take a point that's a regular point of a function, then we can apply the implicit function theorem. So by the implicit function theorem, because A is a regular value, there exists a chart phi that goes from a neighborhood of X into Rn, such that when you look at F, well, first of all, let's say that phi of P is 0. And when you look at phi, F composed with phi inverse of x1 to xn, this is going to be x1 plus A. Okay, that's one of the ways that you can see the implicit function theorem. Okay, so like you're at A if and only if the first slice is 0. So that's one of the incarnations of the implicit function theorem. So now we can just consider the chart. So we obtain a chart which is just phi, the actual phi, restricted to, say, the preimage of A plus infinity intersected with U. So this guy here will take, let me call this set U tilde. This will take this U tilde into Hn. Okay, so maybe I can draw a picture, but my picture is if this is my function, let's say this is my manifold X, and here's my function F, and this is A. So by the implicit function theorem, I can take a set U such that in these charts, basically the function is just the first coordinate plus A. And then you just take the intersection of this with this set, which is relatively open because the function F is continuous. And that will give you the chart that you want. So this will give you a chart into Hn. Like this. Okay, so that's basically the proof. Okay, so I guess we prove that this guy here is a manifold with boundary given by exactly what lies above A. Okay, I guess let me say that the end of the proof is this. Any questions about this? Okay. You guys still there?
Yes, you are.
Okay, valeu. Okay, so now let's talk about the tangent space. Okay, so let's define the tangent space. Let X be a manifold with boundary. So as usual, we can define the tangent space using derivations or using curves. So it's usually easier to just use curves. But now if we're on the boundary, we can no longer think of a curve as something that, goes from minus epsilon to epsilon that's centered at a point. So what are we gonna, what exactly do we mean? So if we take a point in X, a curve centered at P is a smooth map of the form 0 epsilon into X or minus epsilon 0 into X, such that gamma of 0 is P. So now, basically this is only really relevant if the point P is on the boundary of X. Okay, so if I'm on the boundary of X, then I can have a curve that doesn't have a place to continue inside of X. If this is my X and this is the boundary, in this case, if the curve is like this, then it would be from minus epsilon to 0, or it could be a curve from 0 to epsilon. But when I say that it's smooth, it means that in a chart around P, I can actually continue this curve a little bit. Okay? And, as usual, we can define the tangent space at X to be the equivalence classes of curves centered at P, where the equivalence class is just given by the derivatives are the same in a chart. Okay, so the equivalence relation is given by, gamma prime or phi composed with gamma prime of 0. Oh, I guess I can say it like this. Gamma 1 is equivalent to gamma 2 if phi composed with gamma 1 prime at 0 is equal to phi composed with gamma 2 prime at 0. Okay? And these derivatives are well defined because we assume that this object extends a little bit in the neighborhood, even for the points on the boundary. So of course, if you are so if X is an interior point of X, then there's an obvious bijection. It's a very kind of easy isomorphism between the tangent space of the interior of the manifold with the tangent space of X itself. Because a neighborhood of X is, basically, you can think of a little neighborhood of a point in the interior or in the manifold, the whole manifold is basically the same thing. But the interesting point is that what happens if X is on the boundary? So if X is on the boundary, then it's kind of interesting because the tangent space of X at the point little x is still an n-dimensional vector space. So, let me draw a picture so you see maybe if you have like a manifold like this, this is a surface. So at every point in the interior, of course, the tangent space is two-dimensional. But the point is that when I'm on the boundary, the tangent space is still two-dimensional. Okay, so the tangent space has the same dimension no matter if you're on the boundary or outside of the boundary. Because you can think of here, you have these curves that come in through the interior of the manifold and here. That's the whole point of allowing curves that go from 0 to epsilon and minus epsilon to 0. Okay, but moreover, we actually have a canonical inclusion. So we can actually see canonically the tangent space to the boundary inside the tangent space to x at the points that are on the boundary. So this is only if you're on the boundary, obviously. Okay, then you can see, so here, if you're on the boundary, you can see this tangent space to the boundary inside of the tangent space of the whole manifold. Okay, but of course, the tangent space to the boundary, this is an n-1 dimensional vector space. Okay, any questions about this? This might be obvious to some people, but it's not completely obvious. Okay, so now let's talk about a very nice proposition, which is the following. So let x and y be manifolds with boundary, and let y be a point in the interior of y. So this be, I want this to be a regular value of f and of the restriction of f to x, what I'm going to call the boundary of f, which is f restricted to the boundary of x. Okay. Then the preimage of y is a manifold with boundary. And the boundary of this is the same thing as just the intersection of this guy with x. Okay, so this is, of course, the same thing as the preimage of this is the preimage of the function restricted to the boundary of x. Okay, so maybe I should put parentheses like this. Okay. This is obvious. The real, non-obvious part is this part here. Okay, so any questions about this statement? So, there are a couple of things to notice. Is like one of them is you have to take a regular value in the interior of y. If you take a regular value on the boundary of y, then it is not true that the boundary will be a manifold with boundary. That the preimage is going to be a manifold with boundary. So, that's kind of the first thing. I can give you an example. Actually, maybe we should give an example before the proof. Yeah, and then the other thing is you really need to require the transversality for f and for the boundary. So if you only require transversality for f, that's not enough. Okay, so actually, before the proof, let's just give some examples. examples and non-examples. So I guess the first example is, let's say that you have a function from h2 to r that takes x and y to x squared plus y squared. So this is, so here's h2, just this part here. So then what is the pre-image of 1? Well, the pre-image of 1 is going to be S1 intersected with H2. So this is the pre-image of 1. And you see this is a manifold with boundary. So this is a manifold, and the boundary is these 2 points. Okay, so this is a manifold with boundary. Okay, so you have to check these 2 things. Like you have to check that if you take 1, you have to check these conditions. The transversality of f, that y is a regular value for f and for the boundary of f. So f is a regular value. Basically, you have to see that this f is a regular, that 1 is a regular value of f. That's pretty easy because the derivative is going to be 2x to y. So when this is 1, then one of them is different from 1. But you also have to check that when you restrict to this line here, so when y equals 0, the function is just x squared. Oh, sorry, when x equals 0, the function is just y squared. And this function for 1 is also a regular value of this. So you have to check that 1 is a regular value of f, and you have to check that 1 is a regular value of the function that is given by f of 0 dot, okay, which is just dot squared. Okay. All right, but here's a non-example, an interesting non-example, which is this function that goes from h2 to r that takes xy to x. And look at the pre-image of 0. So what happens here is, 0 is a regular value of f. So, it's easy to see. I mean, every point is a regular value because the derivative is 1, 0. So 0 is a regular value of f. But then when you look at the pre-image of 0, that actually is the whole boundary of H2. So, I mean, this actually is a manifold, but this is a manifold. But the boundary of this guy is not the intersection with the boundary of H2. In fact, this guy is a manifold without boundary. So, this boundary here, in this case, the manifold is this whole thing. So the whole manifold is the intersection with the boundary. So you kind of lost control. And this is because when you look at the function restricted to 0, this function is identically 0. So, it's a constant function, and then 0 is not a regular value because 0 is the image of all the points, which are all critical points. Okay, so that, so 0 is not a regular value of the boundary of f. Okay, so that guys, I guess the first one is an example and the second one is a non-example. Okay, so now let me go back to the proposition so we can remember what it says so we can prove it. So it says, if you take a regular value that's not on the boundary of y, then that's in the interior of y, that's a regular value of f and of the boundary, of boundary of f, then the preimage of y is a manifold and the boundary is the intersection with the boundary of x. Okay. So, well, the proof, I mean, the proof is, pretty much what we did before, for, well, let me draw the proof. So we have a function that goes from x to y, and then you pick y in the interior of y. So this is very similar to the transversality theorems that we always have. So if we have a regular value, if y is a regular value, first of all, we can look at this as a function from, we can assume, we can just take a little neighborhood of y. So now we can look at this local picture. So, we have some neighborhood of hn into Rn, and y is a regular value. And then, I mean, the picture is exactly the same as before, as the theorem when you look at the preimage of A to plus infinity. So you use the implicit function theorem. But the point is to be able to use the implicit function theorem and to claim what we need, you need to look at just f restricted to the boundary. So you need to look at this where u intersected with this hn. So inside of this boundary of hn into Rn, and y needs to be a regular value of this for you to really say that this boundary is going to be a manifold too. Okay, so I'm going to leave the rest of the proof as an exercise because I think it is there's not a lot more, but I think that it might be better to just it's the same argument over and over again, like using the implicit function theorem, writing things, finding a chart. I think it maybe is better if you do it yourselves than if you see me do it one more time. Okay, but what I do want to prove is what happens if you take, when you consider a manifold that is transverse to a submanifold. So that's kind of a generalization of this. So the theorem that I, actually do want to talk about now is, so again, we have x and y manifolds, and we have W, a submanifold, a manifold with boundary. And we have W, a submanifold of Y. And we actually want to assume that neither W nor Y have boundary. So the only one really that has boundary is X. Okay? And then now we suppose that F is transverse to W, and the boundary of F is also transverse to W. Okay, so again, F being transverse to W is not enough. You need the second condition, and to see that this is necessary, just think about if W was just the point, then you would need both things. because transversality with a point is the same as being a regular, the point being a regular value. Okay, then the conclusion is the same as manifold without boundary. So then the pre-image of W is a manifold with boundary, and the boundary is exactly the intersection of the pre-image with the boundary of X, which is the same as, the pre-image of this guy. Okay? So how do we prove this? Well, so as before, first of all, you can look at this, what happens in the interior of X. So, if you're at an interior point, then we have the transversality theorem from before. So over here, we know that, the intersection, if you're over here, the intersection of W with the interior of X is a manifold without boundary. Okay, so the real question happens when you take a point on the boundary, of course. So now let X be a point over here. So a point on the intersection of W with the boundary of X. So the usual argument is when you have a submanifold, what you do is you pick a submersion. Again, it's another incarnation of the implicit function theorem. So we can let pi from y from an open neighborhood of the image of X into R m minus k. So this be a submersion such that the pre-image of 0 is exactly W inside V, W intersected with V. So, for whenever you have a submanifold, so W is your submanifold of Y, so you pick a submersion whose pre-image such that the pre-image of 0 is going to give you exactly W in this neighborhood. Okay, and then now you compose F with pi. So now we, as usual, we compose F with pi. No, sorry, pi the other way around. Pi composed with F. And then now, as in the case without boundary, so as in the case without boundary, we have that F is transverse to W at X if and only if X is a regular point of pi composed with F. And the same for the boundary. So the boundary of F intersects W transversely at X if and only if X is a regular point of pi composed with the boundary of F. And now we can just apply the proposition above, the proposition that we have proved. So now the result follows from the proposition above. Okay, and I guess one remark that's not even about the proof, but just about the definition is if X is a point on the boundary, then F is transverse to W at X, or the boundary is transverse to W at X implies that F is transverse to W at X. Okay, because so this condition is stronger than this condition. And this is because, this condition here, it means that when you look at the tangent space, this condition on the left means that when you look at the tangent space of the boundary and you apply the derivative of the F, this is enough to generate the whole space over here. Like this is complementary, or this spans the whole tangent space of Y, F of X, when you add with W. And this guy here, and so this is of course the same as df. And then this space here is contained in Tx of X. So if this equation holds, then dfx of Txx plus Tf of xw equals Tf of xy. So, the boundary of F being transverse to W at boundary points implies that F is transverse to W at the boundary points. Okay, so of course, that holds for a Y equals a point 2, which will be the case of regular points. Okay, so really, when we say that F is transverse to W and the boundary of F is transverse to W, we mean that in the interior points, you can't talk about the boundary of F. It's just F is transverse to W in the interior points. And on the boundary, what you really need is just that the boundary of F is transverse to W. Okay? So there we go. Okay, is that clear? Any questions about this? Okay. So now let's talk about a version of Sard's theorem. So Sard's theorem. So what does Sard's theorem say? It says, let X be a manifold. So in this case, a manifold with boundary. And let's say, Y is a manifold without boundary. Although this really is not very necessary because you can just remove the boundary. But then the set of Y in Y such that Y is a regular value of F such that F is a critical value of F and or the boundary has measure 0. Okay, so this is actually very easy to prove once we know Sard's theorem. So this is the set of points that are not good to apply the theorem of critical value. So, basically you can take the pre-image for points in Y, which are regular values of F and of the boundary of F. Okay, and it doesn't matter if Y actually has boundary or not, because if it doesn't have boundary, if it has boundary, then the interior points, then the boundary is a set of measure 0 too. So you could just remove that. But anyway, so what is this set? So this set is the set of critical points of F union the set of critical points of the boundary of F. Well, sorry, this is a set. It's not this. This is the critical points. But notice that, as I told you, if your critical point of F on the boundary, then you're also Yeah, so if you're a critical point of F on the boundary, then you're also a critical point of the boundary of F. Okay, so this means that the set is the same as, I only really need to look at the set of critical points that are on the interior of X, because the critical points of F on the boundary are contained in the set of critical points of the boundary of F, because of the kind of the counter positive of this arrow here. Okay, so if I can't generate the tangent space of Y looking at the whole tangent space of X, then there's no way I can generate the whole tangent space of Y just looking at what's on the boundary of X. Okay, so this is because if X, this is because if X is on the boundary of X, and the derivative of dxx is contained but not equal to the whole tangent space, then there is no way that if I just take the image of this guy, I can generate the whole tangent space. Okay? Because this guy is a subset, is a subspace of this guy. Okay. All right, so now we can apply the function f to this. So when I apply f to this, then I get the set of critical values of f or the boundary of f. And this is the same, of course, of now f by this equality, f of the set of critical points of this, of f on the interior, union f of the set of critical points of the boundary of f. But now, of course, this is just, this is the set of regular values, the set of critical values of a function on a, from a manifold without boundary to a manifold without boundary, and the same thing here. Okay, so this is the set of regular critical values of the function f restricted to the interior of X, and this is the set of critical values of the boundary of F. Okay, so we have two sets of measure 0, and the their unions have measure 0. Okay, that's it. Okay, any questions? No. Okay, so now we also have the Thom transversality theorem for manifolds with boundary. Oh, it says the following. So let X and Y be manifolds, such, and W be a submanifold of space of jets. So, I guess I haven't really defined it, but manifolds with boundary, let me emphasize that they have boundary. If you have manifolds with boundary, because, the smoothness means that you can extend it a little bit, then you can talk about jets and everything else as before. So manifolds with boundary, we have jets too. So you can take W, a subset, a submanifold of the jet space. But I actually want to assume, actually for this to make sense, to be a manifold with boundary, I need to assume that W, the boundary of W is empty. So actually, Y doesn't have boundary, and I also want a submanifold that doesn't have boundary. No, sorry, this is not true. Sorry, one thing at a time. So first of all, I want the second manifold to not have boundary. And the reason is because if I take the product of two manifolds with boundary, I don't get a manifold with boundary in general. I only do that if one of them doesn't have boundary. So I assume that the boundary of Y is empty, so that the jet space is a manifold with boundary. And I also want to assume that the boundary of W is contained in alpha inverse of the boundary of X. So, so in other words, the boundary of W doesn't touch kind of the other part of the boundary that has to do with, the derivatives and stuff like that. Okay, so I mean, this is slightly technical, but but you just think, like the zero jet space. I guess to really kind of understand, just think. Well, let me finish the statement of the theorem, and then I'm going to explain. So the theorem is that the set of functions, of smooth functions, such that the kth jet of F is transverse to W, and the kth jet of the boundary of F is transverse to W, is residual. Okay, so I mean, it's not surprising that the proof is exactly the same. You just have to be careful with the boundaries, but the proof, just say, it's an exercise of basically copying the proof of the Thom transversality theorem, but being very careful about the boundary. And I guess the main thing that you have to be careful about, you can already see if you look at zero jets. So when you look at zero jets, the zero jet space of X and Y is X times Y. And you have to really see that, what happens with X times Y is when you, if both of them if both of them have boundary, then the product is no longer a manifold with boundary. So this is a manifold with boundary, provided that one of them doesn't have boundary. So provided that, for example, the boundary of Y is different from 0. And that's true for all the jets, but in particular for the zeroth jet. And one easy example to see this, basically what happens is if you take the product of two manifolds with boundary, then you're going to have these corners. So the places that you're on both boundaries, in those places you don't really have a natural smooth structure that will make the inclusion really an embedding, a smooth embedding. So this is a situation where X and Y have boundary. Then X times Y is not naturally a smooth manifold with boundary. Okay. All right. And a corollary of this is basically what happens for zero jets, which is often where we want to use the Thom transversality theorem for. So this is the elementary transversality theorem. So it says the following. So if X and Y are manifolds with boundary, but the second one doesn't have boundary, and W is a submanifold of Y with no boundary, then the set of functions which are such that F is transverse to W and the boundary of F is transverse to W is residual. And notice that here, this condition of the boundary of W is empty is similar to this condition here, because when you take W is submanifold of Y, the submanifold that you want to look at for the zero jet space is really, X times W. Okay, and then if X has boundary, X times W will have boundary, and the boundary is going to be the boundary of X times W. Yeah. So, maybe I can just write the proof. And then the second one, as usual, you can always oh yeah, so this is actually kind of interesting. You can do it just in the neighborhood of the boundary. So this one's slightly new, but it's not very hard to prove. If you take a function such that the boundary of f is transverse to w, okay, and w has the same conditions here. The boundary of y is empty and the boundary of w is empty. Then, maybe the point here is like you have a function whose boundary is transverse to w, but you don't know what happens in the interior. But you can approximate f to be transverse to to be transverse to w everywhere in the whole interior of x, and not change it in the neighborhood of the boundary. So there exists a sequence Gn of smooth functions such that Gn converges to f in an infinity topology. Gn is transverse to w everywhere in x, and Gn is identically equal to f in a neighborhood of the boundary of x. Okay, so this is very similar to that statement before, but here it's applied to the boundary. You can write the same thing for any closed set in the manifold, but I guess it's the most interesting to look at what happens on the boundary and look and see that I'm assuming a little more. Like I'm not assuming just that f is transverse to w on the boundary. I'm assuming that the boundary of f is transverse to w. Okay, so but that implies in particular that f is transverse to w on the boundary, as I explained before. Okay, so I guess I don't need to write a proof of this corollary. I think it's very much like what we did before, and this number 2 is really like a corollary of the proof. It doesn't follow directly from the statement, just like for the Thom transversality theorem for manifold without boundary. Okay. All right, so any questions? Let's breathe a little bit. If you want me to go back, please say that. I can go back. Otherwise, I'll move on. Okay, so I'm going to continue. Now talking about orientation. So this is something that you probably have seen at some point, but there are different ways to see it. So again, I'm gonna recall what an orientation is and say some words. So first of all, an orientation for a vector space. So let V be a vector space define an equivalence relation on the set of bases of V as follows. So we say that two bases, x1 or xn, are equivalent if the linear transformation that goes from V to V, that takes xi to yi, has positive determinant. So if the determinant of t is bigger than 0. Okay, so that's what it means for two bases to be equivalent. And it's not hard to see because the determinant, if you compose two linear transformations, the determinant multiplies, that given a vector space V, there are two equivalence classes. There are always exactly two. So if you take a basis, you change x1, you change the order of x1 and x2, then you get a linear transformation of determinant -1. So you can always find a non-equivalent one. And given any, all the bases you want, they're either in the same equivalence class in the other one. And if you, apply another one that's not in it, then you get back to it. Okay, so this is, I guess, maybe observation or an exercise. If you've never seen this, you can try to prove this. All right, so an orientation of V is just a choice of such an equivalence class. So an orientation of V is a choice of such an equivalence class. So usually, the way that we choose an orientation is by just picking a basis and kind of writing it as an oriented set. So usually you say, okay, take the orientation that's given by this basis, blah, x1, x2, up to xn. Okay? Of course, when you write the basis as a set, you really mean that, that the order in which you're writing the set matters too. So it's not a set, it's really like an oriented set. Or, I guess you can think of it as an n-tuple, to be more precise. But people usually just write the set, but, you use the set notation, but you're really fixing the order of the elements and not just the set of the elements. Otherwise, it's not well defined, because if you change the order, if you add a transposition, then you change the orientation. Okay, so now let's talk about what's an orientation on a manifold. So that's a little bit more subtle. So let X be a smooth manifold. An orientation on X is a choice of orientation on TPX for each. So we orient all tangent spaces, so that we can always do, but we actually want a local triviality condition. So what does that mean? Such that given a chart for each chart, if I pick a chart that goes, from U to Rn, and my chart, I'm going to write it like this, x1 to xn, we're going to have that, if I look at the bases, d dx1 at P, d dxn at P, I want that either this is oriented, so it's, it's the right orientation for every P in U, or the other one, dd minus here, and then ddx2 dxn is oriented for every P in U. Okay, so what I'm trying to say is, if I look at a chart around, around any point, if I look at any chart, that gives me a diffeomorphism between the manifold and a little piece of Rn. And in Rn, I have a canonical orientation. And, it doesn't actually change on the point. So basically, for every point on Rn, the tangent space can be seen as the whole Rn. So, I have a basis there. So what this is saying is that, I want this orientation to be locally trivial. So I choose one orientation and I want to kind of go around the chart and have the same orientation. Okay, so and here you start to see why this is a little bit more subtle for a manifold. So if you don't have this condition, then you can always, for every tangent point, for every point P, you can just choose whatever orientation you want. But that, you can't be completely random, because you can't jump like from one orientation to kind of the opposite orientation locally. Okay, so basically, if you have, so what that actually is telling you is, if you just pick a point and then you choose one orientation here, so say you choose this one first, this is V1, and this is V2, then in a neighborhood of this point, the orientation of all the other tangent spaces is given by you. So you just have to actually pick one, the orientation of one tangent space, and that gives you an induced orientation in the whole neighborhood of this point. That's what this condition here is telling you. Okay? So in particular, that actually will give you an orientation of the whole connected component of that point. So now, that's what it's basically saying, is that if you actually want an orientation of the whole manifold, you just have to pick one orientation for each connected component of the manifold. But that doesn't actually guarantee that you can do it. It says that at most you have one orientation for each connected component of the manifold. But as you probably all know, there are manifolds that cannot be oriented. So, observation. Not all manifolds admit an orientation. Well, the most famous example is the Möbius strip. So, I think everybody knows this, but you take a band and then you glue it like this. So I can draw another picture. So you take, something like this, and instead of gluing it like a cylinder, you glue it like this. So you take it, you do a flip, and then you glue it. Okay, and this is extremely well known, but if you want, you can try to do this. So by what I said before, if you want an orientation, you just pick a point on the Möbius band. You choose one orientation, say this is the first one, and this is the second one. So red comes first, this is V1, and this is V2. And then when you move this around, that determines an orientation in every point. So what you can do is you can take a loop that kind of goes here, and then it comes over here. So you can think of going here and then coming back. And what happens, is if you kind of start with this guy and this guy, and you move these guys around, when you come back, the green arrow is going to point down, and the red arrow is still going to point in this direction. So when you get here, you get another basis, which has the opposite orientation. So what this is saying you is that there is no way they can orient this Möbius strip. So here in the picture, can do the same thing. So when you come back, you're going to come back with this basis here, and this guy here. When you compare this basis back to this point here with the original basis, the determinant is going to be -1. So basically, the natural orientation, which is the only one you can get that satisfies this property, that has a problem. When you get back to the original point, you don't have the positive determinant. So that means that the Möbius band, the Möbius strip, cannot be oriented. Be oriented. Okay? So this is an example of a manifold with boundary. It doesn't actually matter if the manifold has boundary or not, that the definition is exactly the same. But if you want a manifold that doesn't have boundary, the easiest example, well, there are two, but let's talk about the Klein Bottle. Well, the two easiest examples are the Klein Bottle and the real projective plane. So the Klein Bottle is what you obtain when you look at a cylinder and instead of gluing the two sides, like this to do a torus, then you kind of glue them. You glue this with this. So what you actually obtain is. Let's see if I can draw this. It's always hard, but. Yes, so you kind of obtain this thing. So in other words, you kind of take your cylinder, so you identify this side with this side. So when you glue this, you have the cylinder. But then you identify this side with this side going the other way. That's a Klein Bottle. Okay. And by doing something very similar to the Möbius strip, you can show that this is non-oriented. So you go around the loop and you come back with the opposite orientation. And actually, another way to do the Klein Bottle, and maybe it's a nice exercise if you've never seen, is that you can just glue two Möbius strips together, and that gives you a Klein Bottle. Okay, if you just kind of cut it like here, then you can see, you just kind of glue two Möbius bands together, and you get a Klein Bottle. Okay, so another interesting example is the real projective space. So there are a million ways to look at it, but one of them is you can look at a disk and you can identify the points on the boundary that are x with minus x on the boundary. So that's the same thing as looking at the boundary and identifying this part here with this part here. That's a real projective space. And again, using the same argument, you can show that this is not orientable either. Cannot be oriented. Yeah, the same thing. In RP2, you can actually obtain by just gluing a disk to the Möbius strip. So when you look at the boundary of the Möbius strip, that's a circle. So if you can just kind of glue a disk to close it up, then you get the real projective space. So yeah, so that's what it is. Okay, any questions about this orientability question? And I should say one more thing. So, it's clear, the idea of orientation is clear up to dimension 1. And then I guess we also need to talk about zero-dimensional manifolds in their orientation. So, everything that I've said before, up to here, still true for a zero manifold. So, a zero manifold is just this joint union of points. And then the boundary of a one manifold is, a zero manifold. Because, when you look at H1, then what you have is just, this. So the boundary of H1, is just going to be this point. So at every point in the one manifold with boundary, it's either in the interior or it's a point, and it's going to be isolated from the other ones. Okay, so up to here it's okay. But what about the tangent space of a zero manifold? If we didn't quite emphasize this, but if you have a zero manifold, then the chart is basically just a map from a point to a point in R0. So, it's kind of almost an empty map. So, like a chart is just a map from a point to R0, which is just a point. It's a zero-dimensional vector space, which you can think of as just being the point 0. So it's kind of there's very little content. But one thing that's very important is to look at the tangent space. So the tangent space of a zero manifold, kind of by definition, is just R0. So it's just the zero-dimensional vector space. And what is the basis for the zero-dimensional vector space? Well, basis is just the empty set. So, it's kind of a lot of trivialities, but it's something that's important to say, actually. So a basis of this is the empty set. But we would like to extend the notion of orientability to this case, to the empty set. So here, what we do is we actually say we also want to say that there are two notions of orientability, or there's basically well-oriented and not well-oriented. So basically, we're going to say that orientability here is just a choice of signs. So an orientation of the zero vector space is a choice of plus or minus. So we're going to say, this zero-dimensional space is positively oriented or negatively oriented. So now we can talk about, like points as being zero manifolds, which are positively oriented or negatively oriented. Okay. All right. Oh, and one more remark that I should say, and this is true in any dimension, is that a connected orientable manifold has exactly two orientations. So if it's possible to find an orientation for a manifold, then you can always flip it, and then you have a different orientation. Okay? All right, so now what I want to tell you about is how to find natural orientations for manifolds. So, so far I told you what orientations are, and I gave you some examples of manifolds that cannot be oriented, so non-orientable manifolds. But it's not very clear that some manifolds can be oriented. How do you know even that the sphere is oriented? It's kind of how do you even orient things? So first of all, of course, as I kind of mentioned but didn't write down, Rn has a natural orientation. And that's just given by, any tangent space, the tangent space at 0, for example, is naturally identified with Rn itself. And you can just take the Euclidean basis. This gives you a natural orientation. Okay. And of course, if you take any subset of Rn, any open subset, so if this is an open subset, then it is going to be an orientable manifold. But apart from this, we don't actually know what else to do. So the next thing that I want to say is, remember that a natural way to construct manifolds is to take the pre-image of a regular value. So or the pre-image of a submanifold. And now what I want to say is, if you are given a submanifold which is oriented, then its pre-image is going to have a natural orientation. Okay, but before that, another thing you can say that's even simpler than that is, if you take an oriented manifold with boundary, then the boundary is going to have a natural orientation too. So I'm going to do this thing today, and the other thing about the pre-image of regular values I'll do next time. So I guess I can call this a proposition. So let X be, I mean, it's more like a construction, but let's call this a proposition. Let X be an oriented manifold with boundary. Then the boundary of X has a natural orientation. Okay, I mean, it's kind of obvious that the interior of X has a natural orientation because, like I said, at interior points, the tangent space in the tangent space to S and the tangent to X and the tangent space to the interior are basically the same thing. But on the boundary, they're not the same thing. One is included in the other. So how do you do that? Well, let me just say this proof, but it's really like a construction. So, we have to see, we know that the tangent space to the boundary, so for a point on the boundary, the tangent space to the boundary is contained in here. So now what I want to say is, given an orientation of these guys, how do I get an orientation here? So how do I know if I pick a basis of the tangent space of the boundary, how do I choose a right orientation and a wrong orientation? Well, does anybody have a guess? Or I'm sure you've seen it somewhere, at least in a calculus class. So what you need to do is you basically need to find a complement of this tangent space in here. So you need to find a natural way of complementing this guy in here. And that's what one way to do that is to look at the normal bundle. So there exists a one-dimensional vector bundle over the boundary of X, which is given such that, and then I'm going to call this vector bundle N, such that N X plus Tx is equal to Txx. So you can always find a one-dimensional bundle satisfying this property. Okay? And this is not completely obvious, but it is true that you can always find a complement. And the easiest way to see this is to consider a Riemannian metric and to look at the normal bundle. So if we consider a Riemannian metric on X, you can just define NX to be the orthogonal complement of the boundary of X inside of Txx. And then it's kind of obvious that this holds. And the normal bundle, I mean, it has another nice property, which is that we can find a global trivialization. So there exists a normal vector field. So there exists a vector field that I'm going to call N. So this is a section of the normal vector bundle. So there exists a global section. So this is called such that Nx points outward. So I mean, I guess the only thing you really need is to find a non-zero section. So something that's never zero, a non-vanishing section. But let me actually say, there exists a vector field which doesn't vanish. And this is not, completely obvious, but it is true that there exists a vector field that never vanishes. And the reason is because you can choose, you can define what's called the outward normal. Define the outward normal vector field. How do you define the outward normal vector field? Well, for every point on the boundary, if you look at the normal, the normal tangent space, that's a one-dimensional space, and that basically has two directions: the one that's pointing out and the one that's pointing in. So you can just pick the one that's pointing out, so you can kind of define a curve that's like from minus epsilon 0 into your x, such that gamma of 0 is x, and gamma prime of 0, that's the vector field that you choose. So you want gamma prime of 0 to be in this nx, and you can just choose your little nx to be gamma prime of 0 over the norm or something. And it's not very hard to show that you can do that in a smooth way. So that's your normal vector field. Okay, so if you take this outward normal vector field, or outward normal vector field, then you can define an orientation. You can see an induced orientation. So now if V1 through Vn minus 1 is a basis of the tangent space of the boundary at a point on the boundary, then when you put in this guy, this nx, V1 through Vn minus 1, this is a basis of Txx. So now you can say, now if you have an orientation that's chosen on x, then that means you have an orientation that's chosen on this tangent space. So you can say that this basis here is positive if this basis here is positive. And vice versa, this basis here is negative if this basis here is negative. Okay, and that's well defined. Okay, so for example, let's look at some examples. So if you take your disk, so this is my disk D2 inside, or B2 inside of R2. As I told you, this B2, it has a natural orientation. I mean, it's not an open set. The interior is an open set, so it's clearly the tangent space here has a natural orientation, which just is, the tangent space is naturally identified with R2, and you pick the Euclidean basis. So using this construction, I guess this is the end of the proof. Using this construction, then S1, which is the boundary of B2, has an induced orientation. And what is this orientation? Well, at every point of S1, I have a tangent space. And I need to basically tell you which direction is positive. So I have to tell if it's this direction or this direction. So how do we know which direction is positive, with the induced orientation? Well, you pick a point, and now I'm using this one. So now I have to look at the outward normal. So the outward normal is pointing this way, and that's the first vector. So if I want a basis that's well-oriented with respect to R2, I have to choose this one and not the one going the other way. So I have two choices, but I have to choose the one that I just drew that points this way. So this green one is the induced orientation. So another way to write this, and that's how people usually write, for a curve, you can just think of the orientation as something like this. You write an arrow like this. That's the orientation of the circle that's induced by the boundary of the disk. Okay? Any questions about this? Well, similarly, we can do that for any ball. So this, in this case, I have B3 inside of R3, and then I have a sphere inside of R3, and then I have a natural orientation of the sphere as the boundary of this 3 ball. And what is this orientation? Well, given a tangent space here, I have to tell you the order. So, again, I have to have, if I choose my normal, I have to look at the outward normal, which is a unique vector field. I mean, it doesn't actually have to be with norm 1. It just has to point outside. And then every time I choose a basis, say this guy, I can tell you which one has to come first. And, it's basically, in 3 dimensions, we have this right-hand rule. So this one has to be V1, and this one has to be V2. And then V1, V2 is well-oriented, is a positive basis. Okay, because that has to have the same orientation as the Euclidean basis in R3. Okay, so I'm going to end here for today. So I'll see you for the next lecture.